Hey, morning, everybody. So today we are going to talk and go through the several collabs for a topic of the Bayesian inference, structured Gaussian processes, and hypothesis learning. So these techniques are exceptionally important for the implementation of the active learning experiments, whether it is electron microscopy or something else. And generally, it is very important to understand the philosophy and basic principles behind these methods. So on previous lectures, that was lecture 14, we went through the basics of the Gaussian processes. So we discussed what the Gaussian process is. Basically, it is one of the ways how we can interpolate the function given the number of measurements in certain locations. So the important thing about the Gaussian processes is that they give us not only the interpolated value of the function, but they also give us the uncertainty. So this capability to generate the function itself and uncertainty is actually the key for active learning schemes. So we looked a little bit under the hood of the Gaussian processes, so what is kernel and kernel parameters. And we particularly focused on the role of the kernel and noise priors in the way the Gaussian process converge. So the reason why we did it is because there is a general statement that Gaussian process will always discover the true value of the function. This statement is obviously correct. The only caveat is that depending on how you choose the priors, it determines how long it will take the Gaussian process to discover the true value of the function. And obviously, since we look at this problem from the experimental viewpoint, any measurement is expensive. So secondly, we looked at the Bayesian optimization. So Bayesian optimization is essentially how are we going to explore some parameter space given the some measurements. So if we did measurement at several locations, we are going to choose the point for next measurement. And we discussed the concept of the acquisition function. So acquisition function is essentially how we make decision, or in the language of the reinforcement learning or stochastic optimization, this is a policy. We can choose the acquisition function that favors exploration. So in this case, we would explore the regions with the maximum uncertainty. We can choose the acquisition function that will try to optimize our function in some respect. For example, if we choose the acquisition function that goes for the minimum, we will choose the next measurement in this location. So realistically, for most active learning methods, we need to balance exploration and exploitation. And this can be accomplished through the selection of the proper acquisition function in our Bayesian optimization. Again, the important thing to mention is that we can run the Bayesian optimization workflows using other surrogate models, not necessarily Gaussian process. But by far, GP is probably the most important one. That being said, Gaussian process, by definition, have a number of very significant limitations. And one of those limitations start with the fact that this is purely a data-driven approach. So given the data, we try to reconstruct the behavior of our system based on some general consideration that it should be smooth across the parameter space, or to be more precise, correlated. So if you feel that in this case physics is totally ignored, you would be absolutely correct. So Gaussian process is of course connected to physics on some level, but it doesn't allow us in this pure form to explore the introduce the physical knowledge. So in this lecture, we are going to look at the very important plus of the Gaussian processes, where we can actually add the physical model to be a part of our exploration. But before we go there, let's have a quick look at the Bayesian inference and learn what is the prior distribution, posterior distribution, least square and compare it to the least square fit. So let's go to the first collab. Let me go to the stop sharing this screen and share the first of the collabs that is on the GitHub. And this collab is going to explore and compare the least square fit and the Bayesian inference. So first of all, I mean, least square fit is something that all of us have encountered multiple times. So it's probably the most basic tool across all scientific domains, sort of starting from physics to data science to biology and so on and so forth. And basically, the idea of the least square fit is very straightforward. So imagine that we have a certain number of measured points. So x, y, x is our position in the parameter space. Y is the measured value of the function. So x and y can all be scalars, vectors. It can be pretty much anything whatsoever. So x can be a molecular structure. And we have a function f, which has a vector of parameters theta. So the easiest way to think about it is the linear function has two parameters, a and b, the slope and the offset. So more complex functions can be pretty much anything. So the point of the least square fit is to create the function y hat such that it is as close to the actual measured values of y in the points where the measurement is made. So that's the whole idea of the least square fit. And the way as close as possible is defined by basically the least square mean square difference between the predicted and actual value of the function. So if you look at it as the minimization problem, we try to minimize this loss function, so the difference between prediction and the measurement in the parameter space of the function. So it's very simple. All of us have the intuitive knowledge of least square at some point. There is a tremendous amount of the work. So this is something that scientists have been using for several centuries. So there are great articles on Wikipedia about it. There is a good discussion on the Medium blogs on Towards Data Science of Wolfram Matworld. So it is really straightforward. But let's look at the least square from the perspective of the physics. So in general, the equation does not come from nowhere. So equation represents the physical knowledge that we have. So if we fit our data by the linear function, we of course choose it because this is the simplest function possible, but we also have some idea about what physical mechanism can give us linear behavior. And in some cases, we'll go for the linear case, sometimes we go for parabola, sometimes we will go for totally different functional form. And the interesting thing is that we typically have a physical idea about not only the functional form per se, but we also have an idea about the values of the parameter of the function. So it is very normal to do the physical fit and choose some values in the fit function to be either constants or postulate that they have certain range of possible values. For example, imagine that I want to fit the data where one of my parameters is the speed of light, and the other parameter is the mass of the object. Generally, you expect that you will choose the speed of light as known, and the value of the mass is unknown. But this logic can be a little bit misleading. For example, there is a very famous story about the exams. I think it was in the French Academy, where people were given a very simple problem. So you're given a string, you are given a iron weight, you are given a clock, and your job is to measure the acceleration of free fall by measuring the oscillations of the simple pendulum. A very simple problem. There was a small trick. Under the table, there was a magnet, which basically means that the force acting on the weight was different from just the Earth's acceleration. And turns out that quite a lot of people do the measurement, but they know that G is 9.8, and they try to write down the G being 9.8. So our beliefs can be actually misleading. So the question becomes, kind of going back a little bit, can we represent the knowledge of physics when we do the least square fit? And the answer is, in some sense, yes. So there are fit packages either in Origin or Python that allow you to do that. But usually you cannot do it particularly well. So you can impose the initial value of the parameters. You can impose some constraint. For example, the parameter can be only positive, but it's not really very precise tool. So as an illustration, let's play with the least square fit using the SciPy, which is the basic Cython library. And let's choose a very simple example of the function, which is simply the function which has a discontinuity. So we define the function that has two linear segments, a times x plus b, c times x plus d, and it has a jump point. So just to plot the function, this is how it looks like. So as before with our Gaussian process case, we define the observations of the function. So these are the locations where we take the measurement. And we also provide the ground truth. So as usual, what we try to do is, given the measurements, we try to reconstruct the ground truth or kind of our predicted function. And we want to find out how close to the ground truth we can get. In the real world experiment, we of course don't know what the ground truth is, but simulated data allows us to explore that. So as before, we define our measurement function, which has some noise level, and you have already seen many times that if our noise level is low, then our measured points are very close to the ground truth. If our noise level is high, then they're a little bit off. And of course, ground truth is ground truth. Now, let's see how we would fit this function using the least square. So if we want to fit a function by function, we of course need to define a function that we want to fit with. So in this case, we call it a jump function, which has exactly the same functional form as our original function. The difference is that this is the ground truth. This is something that we know the parameter of. Then we define the function which has exactly the same form, but in this case, we don't know the parameters. Notice that in this case, we already make a very strong assertion that the function that we use to fit is exactly the same that the function that generated the data. Of course, it can be different, and we'll see the example of that. Now let's try to do the fit. So the way the curve fit is done in the SciPy is using the function curve fit, where you basically provide the value of the functional expression. So this is the function that we want to fit with. We provide the values of x, we provide the values of y, and then we provide the values of the vector of initial guesses. So the way it's going to work is that it's going to evaluate the loss function given this initial guesses, and then it will try to use the gradient descent or any of the optimization algorithms, trying to go down to minimize this loss function. So this is basically all there is to it. The outputs would be the optimal parameter and the covariance matrix, and then we basically can generate the answer. So look what happens. So interestingly enough, once I fit the very simple data generated by the process, which is two linear segments with a jump, by the same function, what I get is completely off. So you can see that the jump is not where it should be. The jump is the totally different location. So let's experiment with this a little bit. So for example, I can make the noise considerably higher. For example, I can make the noise 0.3. So if I do that and I perform the same fit, you can see that jump is exactly again in the wrong locations. And if you look at this by eye, so imagine that you know that the data corresponds to the two linear segments with the jump. You are given only the measurement point. Algorithm didn't do such a bad job after all. It's a very plausible answer. This is one linear segment, this is the second linear segment. So why did it happen this way? It happened this way because the least square fit does not necessarily converge to the true minimum. It can converge to the metastable minimum. We, of course, can improve it. For example, that's the reason why we have this option of selection of the initial parameter values. So our parameters are A, B, C, D, and the last is the jump point. So if we change our initial guess for the jump point to be around 3, see what happens. So in this case, the algorithm said, you know what, I'm comfortable with the jump point being a 3, but now I think that this is one linear segment, and this is a second linear segment. And if you look at the data, you can see that that's actually a very good fit. That said, the true jump point is about 2.1. So let's set the true jump point at 2.1 and see what happens. So in this case, the fit is correct. So notice that given the data, and even given the fact that we know the true value of the function, we can get drastically different fits. You can argue that, okay, if we collect more data, we will get a better fit. I fully agree with you. So if we collect the better data, meaning either more data points, or if we collect the data with the lower noise, the fit will become more stable. But let's face it, in most experimental situations, reducing the noise of the measurement, I mean, sometimes it's possible, but typically it is very, very expensive. If you work with the microscopy, you know that microscopes are already positioned in the rooms with exceptionally low noise. And to a large extent, the noise level of the room determines how well your microscope works. So the typical price for it is about from $500,000 to $1 million per building the enclosure for the microscope. So if you have a $5 million electron microscope, that's a justified investment. If you have a much cheaper scanning probe microscope, it becomes very difficult to justify the building the room, which is 3 times more expensive than the microscope. So just reducing the noise can be not straightforward. Increasing the number of the measurement point is typically the better strategy. However, first of all, it costs you time. So you need to spend time doing that. And time means money and effort. Second problem is that in many cases, we cannot just ramp up the number of measurement points because of the phenomena such as beam damage or the damage to the probe. So that's also not something that we can do indefinitely. And even from the mathematical viewpoint, there is a tricky thing about the measurements that we typically postulate that the noise is Gaussian. So Gaussian noise will average out. The more we take the measurement, the smaller the noise becomes, kind of goes as 1 over square root of n. Unfortunately, there are other noises in the physical system, for example, so-called 1 over f noise. So this type of noises don't average out. So even if we could continue measurements indefinitely, at some point, the non-averaging noise sources will kick in. So, I mean, if you can do it, great idea, but that's not always possible. So what can we do about it? And this is exactly where the Bayesian inference comes to play, comes to help. So let's look at how it works. And before we go there, I also written down several exercises that you can play with this fit, just an idea to figure out when things converge, when things don't converge. So what does the Bayesian inference allows us to do? So first of all, let's kind of start with a little with the hands-on stuff. Install the NumPy and install the GPacks. So import the relevant libraries so that our environment is ready to play with the Bayesian inference. And then, as before, we generate the data set. So in this case, sort of nothing new. You have already seen it for the GP and the Bayesian optimization. Now, what is going to be the difference? So this is data set. I have chosen relatively small noise values, exactly the same function. Now, what are we going to do, and what is defining aspect of the Bayesian inference is that we introduce the probabilistic model. So in the least square fit, we define the functional form and we define the initial guesses of the parameters. So we define the function and one value where we want to start our gradient descent or any other optimization. In the Bayesian inference, we proceed a little bit differently. We still define the function or functions, so we can have several of them. And we also define the priors on the values of the parameters. And this definition of the priors, or this capability to define priors, it's something that is both uniquely makes the Bayesian inference, Bayesian method incredibly powerful. And this is also what is traditionally used as a criticism towards the Bayesian inference. So a strong line of criticism for maybe the last 50 years against everything Bayesian was that if you define the prior, you already have to introduce the prior knowledge of the system. And the typical criticism in the statistical community is, okay, where would the priors come from? And interestingly enough, there were quite a lot of strategies to kind of create the priors. And the true answer is that if you stay within the statistics, purely statistics, you cannot. Priors come from the physics of the problem. Priors represent the prior domain-specific knowledge that by definition is not available from the purely data perspective. That's how we add the real world to the fit. So what is the prior? The prior basically defines what is that we know about the parameter before the experiment, and typically we represent it as the distribution. So the distribution, the classical priors can be either something as simple as normal distribution. So we say that this particular value we expect it to be 0 and have Gaussian distribution with the width of 1. So this is relatively weak prior. So we essentially say that we don't know much. If we are very confident about the value of this parameter, we can still say that, okay, it is Gaussian distribution, but the width is 1 over 10,000. So in this case, that's almost equivalent to saying that this parameter is essentially fixed. We can use different distributions. For example, we can say that we use the normal uniform distribution. Uniform distribution will mean that the parameter can change within some interval and not go outside of this interval. And the distributions can be even more complex than that. So we can choose the bimodal distribution or trimodal distribution. Where would they come from? In many cases, they come from combination of prior knowledge and intuition. For example, if I want to use the prior of the speed of light or the mass of the electron, I will simply use the normal distribution where the mean will be the tabulated value and the dispersion would be the error bar that you can find in the textbook. If I use the prior for something related for the experimental measurement, then I will give the uncertainty related to what I believe is the prior error. If I use something, for example, the polarization in ferroelectric material, then my prior would be bio more complex, like for distribution function with the 4 maxima. And I know that because polarization can have either 2 or 4 possible orientation. So in other words, this is a great way to introduce the prior knowledge in the analysis and do so in the principled manner. So if you hear an argument that Bayesian inference and Bayesian methods are domain specific, that's absolutely true. And this is its strength. It's not a weakness. If there is an argument, oh, but we have to speculate about the priors are, that's also true. But the truth is that whenever we do the analysis of any real world problem, we always make assumptions like that. The only thing is that we make this type of assumptions and approximations either implicitly, and they remain outside of the paper or record or analysis workflow, or we make them explicitly. If we make them explicitly, that means that we can actually trace them and we can go back and analyze where things went wrong. If it is my gut feeling versus your gut feeling, that's not a very good way to compare things. So to summarize, Bayesian inference requires prior knowledge, and that's its strength. Now, how does it work practically? So we define the possible probabilistic model. So in this case, let's define two functions. One function, which is incorrect function, so sigmoidal function. So in this case, this is its functional form. We have 4 parameters from beta 1 to beta 4, and we define the priors for all of these parameters. And then we create the piecewise function, which has parameters beta 1, beta 2, beta 3, beta 4, and the jump point. And we also have the distributions of these parameters. So just as illustration, notice that I have chosen the uniform distribution for the parameter t. And let's, in the beginning, set this parameter to be 3.7. So from 0.5 to 3.7. So as a reminder, it's always a good idea to check what the distributions really look like. So this is what it is. And then what we do is, the way we realize the Bayesian inference fit, very simple. We define the model. We define the model parameters. We define the random keys. So this is something that JAX wants. And then the way we do the fit is basically we just say, define the model, and using the kind of structured model and model parameter, and then take our measured data, X and Y, and just fit this model. That's it. So the parameters that you need to pay attention to, the number of warm-up points, number of samples, and number of chains, these are the parameters that define how the Markov chain Monte Carlo works. So for the time being, it does matter. So we are going to ignore it for the time being. It's sort of going a little bit deeper under the hood than we need. So what does the model give us? So at the first glance, it gives us the list of the parameter values, meaning mean, STD, median, then a bunch of other parameters, and then gives us R hat. So R hat is an important parameter that you need to keep an eye on, which basically means that if it is 1, that means that our fit converged. If it is considerably larger than 1, then it is danger, Will Robinson. So then something didn't work out. So the interesting part that we care about is the values of mean and STD. Mean is very easy to understand, either mean or median. So you can say that this is essentially something almost something that can be used as the point estimate of the parameter value. So in some sense, it's the result of the fit. But then you notice an interesting thing, that in this case, mean generally means that we have a distribution, right? It doesn't mean that we have one parameter. And that's exactly why, because when the Bayesian fit works, what it starts with our prior distribution. So what we think the parameter values were before the experiment. And based on the experimental data, it updates to give the posterior distribution. And posterior distribution basically means that given the data, now our beliefs have changed. How does it connect to the classical fit? So there is a general principle that if you have a lot of data points, the results of the Bayesian fit and the results of the classical least square fit would be pretty much the same. So the same principle that if you have a large number of data points, then Bayesian fit and the Bayesian methods and the frequency-based methods give the same answer. So they kind of converge together. That's great because this is essentially a sanity check. However, if the number of the data points is limited, Bayesian approach and the frequency-based approaches, or Bayesian approach and the functional fit approaches, behave very differently. Because in the classical frequency approaches, we just open up the uncertainty interval. In the Bayesian approaches, the role of the prior beliefs becomes progressively more important. But at the same time, we kind of generate the data, generate the answers. Now, let's see what else Bayesian fit have given us. So the way we look into the prediction is we generate what is called mean and samples using predict method in the GPACs. And basically, what the mean is what is called the predictive mean. It means that our algorithm has found all the way the function can behave and found the average. And the samples is the examples of these predictions. Now look how it behaved. So now instead of just one fit that is on average, the algorithm gave us all the fits that are consistent with the priors and the experimental data. And look how beautiful it behaves. So essentially, in this case, the algorithm says that our linear slopes are more or less constant for all the realizations of the function, but it was not able to find out where is the position of the jump. And this makes absolute sense, because in the function like this, if we know that the dots are our measured points and the line is the ground truth, there is no way that based on the data, we can say where the jump is between these 2 points. We just cannot do that. In the least square fit, it will put the jump whatsoever. There would be no way for us to ascertain whether it worked well or not. But in the Bayesian inference, it basically tells us that the jump can be anywhere between these 2 points. And what's interesting is that as the result, our predictive mean function goes like this blue line. So you can see that it is not, doesn't have a jump, it has a slope, because you essentially average all the possible jump positions. It's actually pretty cool. So the question is, how much can we jump? How much we can believe this prediction? So in order to do that, all we have to do is to define the standard deviation between the sample predictions. And we see a beautiful picture. So the crosses our measurements. The blue line is the ground truth. So this is something we want to find, but of course we cannot, because this is not available in the experiment. The blue line is our posterior mean, and the red bubble around it is the model uncertainty. So notice that in these regions, our uncertainty primarily comes from the aleatoric noise. So the data comes with the noise. Bayesian inference model recognizes this noise. It gives us essentially the uncertainty interval for each location. But in this case, the uncertainty is much higher, simply because the model doesn't know where the jump is. And this is really amazing. So what can we do with that? So in fact, we can also connect the GPACs to the classical Bayesian analysis library. So in this case, the RVs, which allows us to get insight in the posterior distribution of the parameters of the function. And the way we can visualize them is the joint distribution between the different parameters, for example, the T, beta, beta1, beta3, and so on and so forth. And we can also visualize the unimodal distribution. So what does it tell us? So as you can see, these distributions are not particularly detailed. So first of all, they're fairly narrow. And secondly, they all look like Gaussians. So this is the case where the least fit would work reasonably well if it converges. But the interesting thing is the distribution for parameter t. So notice that it goes from 2.1 to 2.38. And the reason why it goes between these two values is because this is exactly the positions where the jump point position could be. So you can also learn quite a lot from the joint distributions between the parameters. So in the joint distribution is marginalizable, meaning that distribution can be represented as the product of the marginal distribution function. Then they are not dependent. If it kind of goes like this, then knowing one parameter can enhance your knowledge of the other parameter. So this is kind of the usual way we analyze joint distributions. Before we go further, let's play a little bit more and see what happens if we take a much noisier function. So in this case, we took our noise as 0.15. So let's choose the noise being much higher, so 0.35. So notice that the experiment is much noisier. So you know that in this case, the least square fit would have worked much worse. Let's see if the Bayesian inference will work and what it will get. So this is our warm-up. This is our sampling. So for all, we are going to do it 5 times for kind of getting 5 chains overall. Let's look at our prediction. So what you see in this case is that, first of all, things actually worked reasonably well. So first of all, notice that we found the jump still in the right place. Our values of the parameters are off, which are not surprising given the noise level. And we can basically see how the uncertainties behave in this case. So again, we have the uncertainty due to the data. We have the uncertainty, due to the noise level. We have the uncertainty due to the position of the jump. But again, things worked reasonably well. So can we throw the Bayesian inference off? Yes, very easily. If we choose the wrong values of the priors, for example, if in this piecewise function, I choose the value of the prior to be from 0.5 to 0.7. So what it means is that I have the reasons, meaning the prior knowledge, that informs my belief that the jump can be between 0.5 and 0.7. More importantly, this prior is restrictive. So by definition of the uniform distribution, I cannot get outside of this interval. So in this case, things are not going to work particularly well. So you see that the Bayesian inference still worked. It tried to make as good fit as possible, but it really cannot predict things very well because I have chosen the wrong predictive prior. And to some extent, you can conclude it from the way that the model uncertainty behaves, because it's essentially uniform everywhere. So of course, if we come up with this type of approaches, it will not work even if our noise level is much, much smaller. So if I make the noise 0.05, so in this case, the data is perfect, but I still force it to be from 0.5 to 0.7, I can, of course, show that things are not going to work particularly well. So let's see how it converges. So as you can see, in this case, it tried to feed the data as best as it could. And since we did not allow it to converge to choose the right value, it basically produced the wrong answer. So the usual principle with anything related to the probabilistic models and Bayesian inference is that having prior knowledge usually helps you to discover the right model. So in the example that I've shown, the Bayesian inference will work much better in these scenarios when the noise is high and the number of data points is low. So it will work, it will converge to right answer when the least squares stop working. However, if you have a prior knowledge that isn't correct and which comes with a high degree of belief, then of course you will get the wrong answer. So this being said, let's try one more experiment when we define the prior to be reasonably broad. So we again change it to 3.7, but where we choose the high noise, so 0.15, and where we take the reasonably small number of points, for example, 10. So see what happens in this case. So this is our data set. That may be, let's take noise a little bit higher. So let's make it 35. So this is our data set. So again, we define our functions, and again, we perform our fit. So let's see what happens in this case. Okay, once we run it, now looks, something interesting has happened. So notice that now our predictive mean function is not line anymore. So this part is a linear segment. This part is kind of the linear segment. But here you start to see that our predictive mean is actually kind of almost parabolic. So why did it happen? It happened because at this point, we cannot find exactly where the jump is. So the jump can be between these 2 points, or the jump can be between these 2 points, or the jump can be between these 2 points. And remarkably, we can visualize this behavior if we look at the posterior distributions. So you can see now that our t, so let's look, this is our value of the position of the jump point. You can see that it can be between 0.5 and 1.5, so with about 20% probability. It can be between about 1.5 and 2.5 with about 50% probability. And it can be between the 2.5 and 3.5 with something like 3% probability. So basically, the great thing about the Bayesian inference is that given the data and given our model, we can say that the jump can be here and ascribe the probability to this event. We can say that it can be here and ascribe the probability, and it can be here, and we can ascribe probability for this event as well. So in this case, this is perfectly traceable. So if all of us have the same data and same priors, we would be able to reproduce these results and quantify this uncertainty. And of course, as I said, it does depend on prior. If we choose the priors for position of the jump point more precise, more limited, in a more limiting fashion, then of course this behavior will change. Now, the last thing that I want to show you about the Bayesian inference is what happens if we have multiple models. So for example, for this particular function, we can have linear model, we can have sort of simple linear model, just a line. We can have 2 line segments, line with offset. We can have the power law model. We can have exponential model. We have sigmoidal model. So how do we choose the right model? So there are 2 ways to deal with that. One way is to build so-called hierarchical Bayesian models, where we take each model, we ascribe the probability for each model, and then basically we choose, then the probability of the model also becomes a prior. So when our Bayesian optimization, our Bayesian inference process works, we basically update the probability of the model and the model parameters at the same time. This is doable. However, that tends to be reasonably computationally intensive. So as you notice, even with the modern computers, Bayesian inference is not particularly fast. So we cannot really use it to fit the 10,000 point data set. We have to kind of come up with more creative ways of doing that. The second way of doing it is through so-called the widely applicable information criteria. So basically, the way it works is that we create the fit of the models and the fit of their priors, so we cannot have them separate. We fit the data using all the models, and then we use the VIAC in order to compare them. So the good thing for us is that the GPAX or any other environment, for example, PYMC, will be compatible with the RVs. And RVs already has the function that takes the Monte Carlo traces for all the models and basically compares them directly. And then it ranks them based on which model works better. So in this particular case, you can see that for this particular data, the sigmoidal model seems to be working better because, again, we have high noise and not enough data points. And basically what we can do is to try to compare the prediction with the best model and compare the results and make a prediction with the second best model and also compare the results. So, then it goes to the point of our judgment, which of those seems to be better. So going back to the formal Bayesian world, there are more sophisticated strategies for doing it. There are quite a few books, good books on it, including Oswald Martin and so on the PYMC. But I thought that, but this is a kind of good introduction into how the Bayesian inference works and what it does. So before we go forward, do you have any questions about this? Okay, if not, then let's make the next step and talk a little bit about the structured Gaussian processes. So, so first of all, the important point here would be that structured Gaussian processes is not something that you would be able to read about in textbooks, or at least in any form that makes sense. So generally, there are several excellent books out of there talking about the Gaussian processing methods. So my favorite is the one by Roman Garnett, Bayesian optimization. It's a really great perception, a really great presentation of what Gaussian processes can do from the perspective of the data scientists. There are several other books out there, McElrath, Rasmussen, whatever, sort of the classics one. But generally, all these books tend to say one very important statement. Once we consider the Gaussian processes, we assume that this is a function or multivariate Gaussian distribution that has a zero mean and some form of correlation. This correlation is given by kernel, and then they go on to explore the behavior of the Gaussian process as the function of the kernel. So what does kernel do? In all the textbooks that I'm aware of, there is usually either paragraph or at best half a chapter that says that the mean function in Gaussian process is highly domain specific. It affects how the Gaussian process will behave. However, given that it is domain specific, we are not going to explore it in detail. And from the perspective of the data science, that's a very correct approach. The mean function is domain specific. It represents the physics of the problem. For one set of problems, it would be one mean function. For another set of problems, it would be a different mean function. But that obviously creates a problem, because if you want to use the Gaussian processes with the non-zero mean function, you don't have nearly any code bases or guidelines comparative to the work on building the beta kernels. So in other words, you're effectively on your own. And the good thing that sort of one of the factors that have driven the development of the GPACs by Maxim Ziadinov a few years ago was this driving force to combine the Gaussian process with the structural model. We know the structural model that Bayesian inference and generally structural models represent the physics of the system, but Bayesian inference in the pure form is usually very brittle, so you cannot use it for inference very well. So Gaussian process in the pure form are very powerful and flexible and stable and so on and so forth. However, they're purely data-driven. So if we combine the Gaussian process with the structural model, we get something that both has the prior knowledge of physics in the form of the mean function, and it has the flexibility of the Gaussian process and the capability to provide the uncertainty, which allows us to build the Bayesian optimization workflows on top of that. So this is exactly what we've done. So this is the kind of cliff note type of definition of the Gaussian process augmented with the structural model. So the new thing is that there is a mean function. The way that you update the data changes. So this is the update of the normal Gaussian process. This is how the update of the Gaussian process with the non-zero mean function looks like. This is essentially looks like mathematical mumbo jumbo, and it is. So this is not something that you ideally want to do. So the idea is to have the hands-on experience rather than get into the depth of math. But the important thing to realize is that now we have the Gaussian process where the mean function is the probabilistic model. So as you remember, for the classical Gaussian process, our prior predictive distributions look like this. It's the functions which have the zero mean, but have some correlation. If we have a structured Gaussian process, then our prior predictive distributions start to look like this. They're essentially the probabilistic model, and we can choose a model to be fairly complicated. For example, we can choose the model that has some offset, that has two peaks. The peaks have the Lorentzian shape. We know that the offset has uniform distribution from -10 to 10. We know that the peaks have the amplitude, width, and position, and we know that we can provide the prior distributions for them. And we can provide this distribution to be common or separate. For example, I can say that for peak 1, I expect the position to be between 0.2 and 0.4, and for peak 2 between 0.6 and 0.8. So that's exactly the same flexibility of the Bayesian inference as I've shown you before. So before we go to the collab, let me show you what a difference can structure mean function make even in the simplest case. So for example, imagine that I have a function that looks like this. So the ground truth is the power law here, a linear function here. The crosses are initial measurements. The dots that appear is our automated experiment. So we try to discover this black function. And the red is the GP reconstruction. So notice that if I try to fit this data in the active experiment mode by the classical GP, it doesn't work particularly well. So in the beginning, it kind of discovers what happens here and what happens here. But after that, it really cannot reconstruct this jump. And the reason why it cannot reconstruct this jump is very straightforward. So it cannot reconstruct it because the correlations are given by the kernel. Here, the jump is very abrupt, which basically means that the correlation length is actually small. But if the correlation length is small, the Gaussian process thinks that the correlation length is the same everywhere. So the smaller it makes the correlation length here, the more measurements it needs to take here and here to make sure that there are no other jumps. This is actually a very big problem, because if we use, so it's not only the academic example, this is actually the real world example. Because if we try to use the Gaussian process in order to explore the image, even the image space where we have a sharp domain wall, we have this problem. If we try to explore the phase diagram, either in theory or an experiment, we are going to have exactly the same problem. So for many real problems, real world scenarios, Gaussian process will require the amount of data kind of sort of comparable with the grid search if our parameter space have these rapid jumps. Obviously, we are not the first one to recognize this problem. So there are kind of a lot of ways how the Gaussian processes can be adapted when you simultaneously segment your parameter space and do the GP in the segmented parts. But it turns out that introduction of the mean function actually helps us to resolve this problem. So if we create the mean function that has only one jump, then in this case, the Gaussian process behaves totally differently. Look what happens. So in the beginning of the fit, it finds where the jump is. And after that, it basically spends the remainder of the experimental budget to refine the behavior of the stales. So in this case, we provided the physical knowledge that there is a jump, and we gave our GP algorithm flexibility to describe a single jump in the system. What's interesting is that it actually will work if there is more than a single jump, but that's a kind of interesting example of how things behave if there is more than one, if the function is partially correct. And we'll get to this point. So would it work in more than one dimension? Of course it will. So this is the example of the exploration of the phase diagram for the two-dimensional system. In this case, it's a physical model, a physicalizing model with the nearest neighbor and next nearest neighbor interaction. So this is our ground truth phase diagram. So this is magnetization. So the yellow region here is 1. This is antiferromagnetic phase. So here magnetization is 0. This is frustrated phase, it's also 0. This is the high temperature paramagnetic phases. So as you can see, if we try to explore this, so this is the ground truth. If we try to run the Gaussian process model with the 30 exploration steps, you can see how it explores this parameter space. It starts here, goes here, goes here, goes here, here. So it kind of explores the space almost uniformly. It obviously spends a lot of time on the borders of our parameter space because this is where the uncertainty is usually highest. And this is how the reconstruction will look like. So it kind of generally found the right region. So the yellow is in the top right corner. But of course, there is no sharp boundaries. There is a very diffuse transition. So we kind of learned something, but nothing to write home about. So this is how the structured Gaussian process will look like. In this case, we introduced the probabilistic model that basically says that magnetization can be either 1 or 0, and the boundary between 1 and 0 is relatively sharp. Look what happened. In this case, the algorithm very rapidly found out that these are the regions where the magnetization is 0. This is the region where the magnetization is 1. And then it spent most of its experimental budget exploring the boundary between these two regions. Is it perfect? No, it's not. Because, for example, we were not able to find this region where the magnetization is kind of slightly more than 0. And we didn't find it because that was not a part of our structural model. So we need to be careful about what type of questions we ask. But overall, this is far more accurate. So it's the same experimental budget, just 30 points. So compare our prediction here and our prediction here. So a clear example that knowledge of the structure gives us very huge advantage. So let's see how it works in practice and go to the second collab of the day, which is called 3 GPAX SGPA. So it's in the same folder on the GitHub. So let me share the screen. Here we go. And let's see how this structured Gaussian process works. So the beginning is the same. So we have to install all the relevant libraries, including GPAX, NumPy, RVs, and so on. And while it's installing, we, again, as usual, define our model. So you by now already recognize this code. So it is the piece1 function. The only thing is that we choose it to be x power beta 1 on the left of the switch point, x power beta 2 on the right of the switch point. And this is how the function looks like. So the next thing we do is we try to reconstruct this function with the standard GP when the mean function is 0. Again, we define our priors for noise. We define our priors for kernel. So remember that this is a very important thing to do, and we always should keep track of it. So never rely on the default values of the parameters, because the default values remain the same, but your experimental data can have different parameter values. So the way the default values affect you, if you measure your concentration in percent versus in fraction, would be very different. So let's run the Gaussian process fit. So as before, this is just 3 lines of code. So we create the random keys, we create the one-dimensional model with matter and kernel, and whatever priors we've chosen for kernel and noise. We fit our data, and as you can see, the result is actually fairly pitiful, right? So these are our experimental points. This is the fit the Gaussian process have done. And the red gives you the uncertainty. So it didn't work. And the thing is that it could not work because this function have very rapid jumps, and the Gaussian process basically tries to describe it by the same translation invariant kernel. So that doesn't work very well. So now let's try to do the same thing using the possible models that we are going to use as the mean functions. So now rather than using the GP with the zero mean function, we try to define the GP with the mean function that represents the physics of the problem. And we are going to define two functions, one function which is correct, so it has the right functional form x power beta 2, and the second one which is only partially correct. So the second function is the linear x times b, and the second is segment is x times c. So correct function, incorrect function. Of course, the model is incorrect. The model is incomplete, sorry, unless we have the definitions of the priors, because otherwise it's not a probabilistic model. But we define the priors, and then we run our structured Gaussian process for both of these models. So the way we do it is that we define the list of the mean functions. We define the matching list of the priors to the mean functions. We define the loop when we zip them together and then basically evaluate it on the matching list of functions and list of priors. Then we compare the results. So again, the way the code works is just 3 lines of code. So we create the model, we fit the model, we make the predicted mean and sampled predictions, and then we plot the data, and we plot the mean function, and we plot the sampled predictions. Look what difference it makes. So again, this is the Gaussian process. Didn't work particularly well. Notice that, by the way, that predictive uncertainty in this case is going to be fairly low. In fact, the predictive uncertainty here is very, very small, and it becomes large only here. So if we run a classical Bayesian optimization based on the maximum uncertainty, or if we try to conclude where the model is right or wrong based on the uncertainty of the model, we will not be able to do that. So in this case, the true function and the sample mean are very different, but there is nothing about the prediction that tells us that this is a wrong model. So that said, if we introduce the mean function, look how it works. So if our function is correct, we have a beautiful reconstruction. So we capture the right behavior on the left of the switch point. We capture the right behavior on the right of the switch point. We, of course, don't know the true position of the switch point. So if our measurement is here and here, we don't know where exactly it is. And look what happens. Our sample predictions basically say that the jump, you can actually see that they are almost uniformly distributed. It basically tells us that the jump can be anywhere between this point and this point. And our sampled mean function goes like this. So it reflects the fact that the function goes up and then jumps. And therefore, this blue curve is essentially the convolution of the fact that jump is position dependent, and the density of the distribution of where the jump is uniform. So it really worked exceptionally well. Now, what is going to happen if our function is partially correct? So it has a jump, but at the same time, the functional form is incorrect. So look what happened in this case. So the algorithm decided that the jump is between this point and this point. So it's not correct, but you can see how it tried to find the jump position. The fact that it couldn't is because there is not enough data. And what you can do is experiment with this notebook by increasing the number of the points and playing with the noise, and see how the simple GP, how the structured GP with the right function, and how the structured GP with the partially correct functions behave. But in this case, you see that it thinks that the jumps is somewhere between here and here. And notice that, as advertised, the structured Gaussian process is flexible. So we chose our mean function to have two linear segments, but the prediction follows the data. It was partially able to balance the data that we gave to the model and our belief about the physics as reflected in the choice of the mean function and the priors we impose on the mean function parameter. So in some sense, it's the best of the both worlds. So what can we learn about it? So we can, yeah, that would, let's see if it works. So we can, as before, analyze the the posterior distribution of these parameters. So, and see where the t is, where the b values, c values, and so on. We can initialize the model. We can compare the different models and see how they behave. So do exactly the same analysis on the structured Gaussian process as we have done with the normal Bayesian inference, and the parameters will have exactly the same meanings. So the next question you can ask is, can we run the active learning with the structured Gaussian process? And the answer is, of course. That's actually the reason why we have developed this whole workflows in the first place. So the way that we do that is is the same as before. So notice that when we go from through these examples from Gaussian processes to the Bayesian optimization to Bayesian inference to structured Gaussian processes to the Bayesian optimization based on the structured Gaussian processes, we go through the same cycle over and over again. We just add new elements on top of it. And in fact, we are going to continue to do that once we go to the variational autoencoders and the deep kernel learning, because many of these concepts build upon each other, and the early ones which are kind of very unusual from a physical perspective, they serve as the foundation for the more complex ones. But anyway, so the way that we run the Bayesian optimization is exactly the same as we've done before. So we define our initial data. So this is our seed data. So remember that if we do the GP or SGP reconstruction, it's basically one-step process. We start with the data, and then given our model, meaning the mean function and kernel, we create the prediction and uncertainty. So when we run the Bayesian optimization, we do this process iteratively. So we take our data, we create the model. So in this case, it's one-dimensional pattern. Now the mean function is piecewise and prior is prior. We feed the model. And after the model is fit, we use the acquisition function. So in this case, it is the uncertainty. So we evaluate the acquisition function over the prediction. And then we choose the next measurement point as the argmax of the acquisition function. Then we perform the measurement, or in this case, it's quasi-measurement over the in this new location. And then we report the process over and over again. So when we run this in the Colab, our measurement is essentially to take a new test point because they're already known, so we evaluated them. In the real world, that's actually the point when you go to the lab or you run the microscope or do something like this. And as we discussed before, the reason why we always prototype these workflows on the dummy models or dummy data is because it's better to spend a few hours in front of the laptop than several days in the lab or running the microscope. So the way that we monitor the process is exactly the same as for simple Bayesian optimization. So we have the number of steps, we have the values of the parameters. Based on the step, the algorithm selects the new point. So we can very easily add here the print function that will tell us what was the next point the algorithm have chosen. And and of course, we can visualize the process of the learning. And after we run everything, we can actually visualize the result. So in this case, I've chosen not to visualize the intermediate step of the process, just in the interest of time and in the interest of time and it's kind of one of those things you can always try as an exercise. But we can easily visualize the overall process of the experiment after it is done. So this is the way we will represent the data. So the crosses are our seed points. So this is our initial measurement. We need to start somewhere. And in this case, we've chosen 5 of them, but it's absolutely not the process, not the problem to choose one. Also, sometimes it's a good strategy to choose the values of the edge end of the interval. So it's kind of up to you. And in fact, in many problems, the way that we choose the seeds actually matters quite a lot. But in this case, we just chose them randomly. And then the way you read it is that the round points have the color corresponding to the step. So the first measurement we do is this point. So initially, it didn't know what is the value of the function of the end of the edge of the interval. So it did the measurement here. The next measurement was done here. Then it was done here. And then it started to explore this location, go back here, go back here. So as you can see, the algorithm progressively started to explore the place where there is a discontinuity, and it kind of made sure to check that things are good here. So it is very interesting and illustrative to play with this notebook when you change the number of points and when you change the noise in the system. So the behavior would be very different, and it's always fun to see how the model uncertainty evolves. Now, let's see how the process will behave if we choose the wrong function. So in this case, it is exactly the same output. So I'm not going to run it, but you can see that the process kind of evolved in such a way that we actually were not even able to discover the right function. So in this case, we explored this part segment and this segment, but the algorithm was never able to discover the correct position of the jump. So this being said, in this discovery loop, we use the pure uncertainty. So this was not, strictly speaking, optimization. This was the Bayesian optimization when we tried to do the pure exploration rather than exploitation. So what happens if we try to run the structured GP when we do the, strictly speaking, Bayesian optimization, meaning that our acquisition function is something like upper confidence bound or expected improvement. So again, feel free to explore this notebook. And what you will see that in this case, we can very easily get trapped in the wrong minimum. So if we choose our exploration strategy to be rigid, we can very easily come to the scenario when the algorithm makes some supposition about where, for example, is the discontinuity. It starts to explore point around this location, and then it can get trapped in the local minima. So there are several ways to avoid it. So one obvious way is to run our Bayesian optimization initially using purely exploratory acquisition function. So you want to explore over the whole parameter space, and only then you go to the exploitation and make it more and more and more greedy. That's one way to do that. Another way is to start with the very open priors on the mean function, or even go with the zero mean function, and then to inject the structured mean function in the process over the subsequent ranges of exploration. So both of these strategies are a part of the human in the loop active learning. So human in the loop active learning is a new field. As you can imagine, it makes sense only in the context of the experimental problems. So in the pure theoretical settings, it's kind of not particularly necessary. It's not very difficult to realize. simply because the way the GPAX is written, it allows you to redefine the model at each step of the process. So as you can see, we at each exploration step, we basically say that our mean function and the mean prior comes from the outside. So they can be changed depending on the stage of the process. So I will show you some examples of how the human in the loop workflows can be designed later. But for the time being, let's just look at the rest of the notebook. So this is how the maximization looked like. So it actually managed to find the maximum in the end. It turns out that we can also run it with a partially incorrect function. So, and interestingly enough, so in this case, I tried to find the minimum. And interestingly enough, it will work. So what happens is that once you start to focus your attention on the place where the minimum is, if you get close to the either true or false or metastable minimum, the algorithm will start to converge. However, if you are unlucky not to get close to the true minimum and your model got thrown away, then you would be trapped. So that's kind of the place where you have to, where the only way to learn it is to experiment with these examples. And since kind of this lecture is fairly short, let me show you the end result of why are we actually going to how we can use the structured Gaussian process and their extension to the hypothesis and their extension to what we call the hypothesis learning. So let's go back to the presentation. And one question that you can ask, that you can ask is how can we use it in the real world scenarios? So first of all, we can use the structured Gaussian process directly as the part of the active experiment. And of course, it's not necessarily limited to microscopy. It can be synthesis, it can be analysis of the theoretical model. In fact, once you develop the algorithm, it's usually a good idea to experiment with the model system and the theoretical models. But again, the setting is general. So a question that you may ask is, what happens if we have several possible models? So in sort of scientific lingo, it would often be called hypothesis. So the hypothesis can be that we have a system that has a first order phase transition, or it has second order phase transition. So it's either or. We can have a hypothesis that in some system, our dependence of the order parameter on the concentration is linear, or maybe it is described by the third order function with no first order coefficient. Again, it is either or. So can we use the Gaussian processes for this kind of scenarios? And the concept that we have introduced in this case called the hypothesis learning, and the way that it is established stems from the observation that if we are lucky to guess the right model in the beginning of the experiment, that usually the right model is more predictive than the wrong model. So in other words, if we speculate if the true dependence of some parameter of some function observation on parameter is linear, then the linear model will allow us to make prediction with much lower uncertainty than the more complex model. The way we can operationalize this supposition is actually in the form of the hypothesis active learning, which sort of combines the basic elements of the structured Gaussian process and the reinforcement learning. It is structured Gaussian process because this is our core model approach. It is reinforcement learning because we essentially give a reward to the model that allows the prediction with the least uncertainty. So how does it work as the loop? So imagine that we have an experimental system. So experimental system can be anything. It can be chemical synthesis. So you synthesize one compound at a time. In this case, your parameter space is basically chemical space of the system. Can be film growth. In this case, your parameter space is the conditions during the growth and composition. It can be a position within the image. It can be some experiment that you run as the non-indentation on IV curve measurements or something like that. Or it can be the combinatorial library, which you choose the location for measurement using the AFM tip, or you deposit the microelectrodes and you choose the location for measurement of a microelectrode. So the only important thing is that this synthesis or characterization or microscopy are sequential. So the outcome can be is a single measurement. I mean, of course, it can be a batch, then things are change a little bit, but let's assume that this is a single measurement. Once we have the single measurement, we send the result of this measurement to the structured Gaussian process. This is our hypothesis learning. So this SGP has several alternative hypotheses, meaning the models with the certain values of the parameters. Given the data and given the choice of the hypothesis, our algorithm does two things. The thing number one is that it updates the parameters of the models. So this is our classical Bayesian inference or SGP update. It also gives the reward for the model that gives a better prediction, and it will start to favor it down the line via the epsilon greedy type of algorithm. And then it also suggests the point for which the kind of the argmax, usual argmax of the acquisition function. It suggests the point for which we want to do the next measurement. So the way this point is selected is very simple. So for model 1, the best prediction would be in one location. For model 2, the best prediction would be in a different, like second location. For model 3, it would be in the third location. So in this case, we choose the one that gives us the biggest reward. So this is how we break the uncertainty when the multiple models compete with each other. So this is a very simple, I'll show you the notebook where this is realized as the next step, but this is how the typical behavior of the hypothesis learning look like. So imagine that the right model is model number 3. However, by chance, the algorithm started with the model number 1, and it ran it several times in the active learning, and it got some idea about the total uncertainty. Then we use the epsilon greedy approach. So epsilon greedy is the best way to, the easiest way to add exploration when we have the small number of possibilities, kind of the non-discrete possibilities. So because of epsilon greedy, we choose the model number 2. This model didn't work particularly well in the beginning, so the uncertainty is fairly large. So it returned to model number 1 because this model gives you better uncertainty. Then it again, epsilon greedy kicked in, it went to model number 2. Again, didn't work very well. So then it tried model number 1, and then because again of the epsilon greedy, it tried model number 3. And model number 3 gave us much better total uncertainty. So and then you see that we're kind of jumping between the model number 3 and models number 1 and 2, but model number 3 always gives us the best total uncertainty, and therefore we conclude that this is the correct one. So this model has the biggest reward. So you can ask, why can we not do that from the very beginning? So why do we actually have this uncertainty and the competition between the model? And the answer is that we have to do it because even if the model is wrong, it can have a very low predictive uncertainty. You already seen the example when the predictive uncertainty is small, but the mean prediction, predictive mean of the predictive function has nothing to do with the ground truth. So we actually have to explore other models because, again, you know what is the ground truth for this simple scenario, but ML algorithm does not. In the real world scenario, you also don't know. You kind of have the same information as the algorithm. How can we use this in the real world scenarios? So the simple example for this would be the selection of the sample for the combinatorial library. So I've shown you this example in the beginning when we have the bismuth ferrite and samarium doped bismuth ferrite. So it's interesting because it spans the whole phase diagram. The problem is that it's a problem for us to choose where is the right location to do the measurements. Measurements are expensive. In fact, it is also the problem even if the measurements are cheaper, for example, using the scanning probe microscopy. So in this case, we can take the topography and PFM images. So here, topography and PFM here, topography and PFM here. You can see that the sample behavior changes. But again, we cannot do the measurements every 10 microns because that will take forever. So how do we use the hypothesis learning in this case? Very simple. So we try to build models. So one model corresponds to the first order phase transition. The second model corresponds to the second order phase transition. And then we run the automated experiment. In this case, it was kind of human executed automated experiment. In this case, you can see that our predictive uncertainty becomes small, but we cannot truly differentiate between the two models. So it didn't work particularly well. Well, it happens. The reason why it didn't work particularly well is because our measured parameter actually goes up as a function of concentration and then it drops down, whereas our models predict that it should be going down either more smooth or more abrupt. So in this case, it turns out that neither of the models is correct. Well, it happens. So this is the second example when it actually did work. So this is the example where we try to understand the polarization switching inside the material. And in this case, we actually have the list of models. So one model is that the polarization switching, the size of the domain is limited by the only thermodynamic factors. And there are some different assumptions about what happens on the domain end. So the second model is that the size of the domain is limited by the pinning of the domain wall. The third model is that the size of the domain is limited by the charge injection. So the best way to create the list of the hypotheses is based on the physical mechanisms and analyzing, so what is the limiting stage? If this is the limiting stage, this is one hypothesis. If this is the limiting stage, this is another hypothesis. And the way the hypothesis learning actually works when implemented on the instrument is that it starts to tell the microscope what to do. So our parameter space is the voltage pulse, magnitude, and duration. And as you can see, the microscope is now configured as the automated scientist that will create the region of the uniform domain. So this is our drawing board, if you will. Apply the bias, then it will scan the surface and visualize the domain. So after it scans the surface and visualizes the domain, it's going to determine the domain size automatically. It's kind of not very difficult problem. And once the domain size is determined, then this information would be passed to our control computer. So in this case, our kind of automated scientists start to analyze the data and think what this data means. And why the algorithm is thinking, we actually delete the domain in order to prepare to the next experiment. So this is probably the first example of the autonomous discovery system implemented on operational microscope and is implemented in the hypothesis learning mode. So this is how you can observe what happens, how this exploration happens. So this is a relatively simple scenario. We have only two-dimensional parameter space, the time and the bias. So in the beginning, we measure several seed points. Then the algorithm start to explore different models and run the experiment, selecting different model as the guide. And after a while, we come to conclusion that it is the third model that is the correct one. So this is great. We, of course, worked for other scenarios, for example, the synthesis, using the same approach, using the theory. I mean, since this is the school about the microscopy, we are not going to go here in detail. The question becomes, it's a little bit philosophical, but it's also very important. So what is that machine learning can do and cannot do? So one thing that you notice that machine learning can do remarkably well is the following. Given the prior beliefs, so our domain expertise, or what we call the probability of theory, and given the experimental data, we can narrow down these prior beliefs to updated beliefs. So we learn more as the result of the experiment. And this is kind of called the contraction of the prior distribution to the posterior distribution. So this is something that machine learning, or specifically Bayesian methods, are exceptionally good at. The problem that what we don't know how to do in general is how to form the hypothesis. So the reasons why we need to have hypotheses is because we cannot go in all directions at the same time. It costs us time and money. So we need to formulate the hypothesis in such a way that it balances what we want to discover with the most likely outcomes. So if we have only one model, then we need to refine its parameters. If we have more than one model, then we need to have the small, preferably small number of these models, so we can kind of have something to suggest the way forward. Formulation of the hypothesis is a very, very difficult problem, which actually borders very closely with the things like artificial general intelligence and so on and so forth. So there may be ways to construct them mathematically. For the time being, we believe that this is based on the human and domain expertise. So this being said, there are two more things I want to show you. So one is, how is it going to go work in the future? So in the future, it is going to work that we have automated experiments where we have the human and the AI basically working in parallel, where AI takes low-level decisions and executes them fast. And the role of the human is basically to oversee the behavior of the agent and basically make a judgment of how to inject the hypothesis or change the balance of the exploitation for the agent. Second thing that we are going to, and again, we are going to talk more about it. Second thing that we are going to do in the remaining 20 minutes or so is to have a look at how the hypothesis learning is actually going to work in the real world instantiation. So let's go to the third notebook, which is also in the folder on the GitHub, and is called the 4GPAX Hypothesis AI. And given the kind of relatively small amount of time, I'm not going to run all of it. I'm just going to guide you through the relevant elements of the code. And basically what this notebook does is it shows you how to apply the hypothesis learning to the toy dataset. So as we discussed, the reason why we need hypotheses is because we cannot run all the possible experiments. We simply don't have time and effort. So it's actually the reason why, relatively speaking, there were not that many successes of using methods like reinforcement learning in the real world environment. So reinforcement learning is very data hungry. If you ever try to train reinforcement learning agent, even for something like a frozen lake environment, it takes a lot of iterations to do that. If you train reinforcement learning to run the tic-tac-toe, it effectively goes through all the possible ways to play this game. If you try to use the reinforcement learning to play the Mario, when the Mario kind of have to jump on Goombas and so on, you will actually notice that most of the time is actually spent to learn the elementary processes, like don't jump on the mushroom, don't encounter the mushroom. So for real world, hypothesis basically summarize the uncertainty in the form that is amenable to check. So there are excellent books in the history of science, for example, Popper on the history of the scientific method, that talk about more detail. When we go to the real world hands-on application, hypothesis is basically one of the competing models. So the way that we run the hypothesis learning is we introduce do some imports as before. We define several helper functions, so they're pretty clear. So to get the result, get the data, plot the results, plot the acquisition function, plot the final results. So nothing nothing unusual here. As you can imagine, it makes sense to go through this notebook only when you went through the in detail through the previous notebooks, because it uses the same code, it just packs it in a more compact and more functional form. So as before, we generate some data, so you will by now recognize this function. And then we define our competing hypothesis. So we define the partially correct model when we have x power beta, and then second segment is linear. We define the second function, which has two linear segments. We define the third function, which actually happens to be the correct one, except that the algorithm doesn't know about that. And as before, we define the piecewise, we define the priors for these models. Again, priors are very, very important. So notice that we can have a function that have the same functional form. So we can have the fourth function, which would also be power law. But if the priors for that function are different and not overlapping with the priors of the third one, it would be a different model. So for example, if we choose the priors to be Gaussian and relatively broadly distributed, the difference would be minimal. But if we choose the priors to be restrictive, like a uniform distribution, then you will see a considerable difference. As before, we define the priors on the kernel. That's kind of never stops being important. Then we define several helper functions that actually will run the hypothesis learning. So basically, all these functions do is keep track of the reward, meaning which model gives the better prediction. So we figure out what model gives is the best one. We keep the record of rewards versus models. We define a function that allows us to switch between the integral and median uncertainty, so that's kind of not a problem. We define our step. So the step in the hypothesis learning basically starts as before. You define the acquisition function, you define how much you want to know about the process, you define some internal parameter for how you deal with the data set, and then you run your cycle of the fitting the model and the prediction of the model, and getting the kind of making sure that the model converge. So, and then you have the second part, which essentially updates your data points. So if you perform the measurement at some location, there is no need to go back to that location as well. We generate the seed points, and then we go to the main hypothesis learning algorithm. So let's look at how it is structured. So we have the certain number of exploration steps. So this is how many active experiments we are going to run. So during the exploration step, we choose only one model. And we choose the model based on our expectation, what model will give us the best prediction. So the second thing that matters is the epsilon. So epsilon is the same epsilon as in the epsilon greedy. Basically, it means that 60% of the time we are going to choose the action that we believe is best, and 40% of the time we are going to choose the random action. And then we have the warm-up step. So during the warm-up step, we evaluate all the models. So just to have an idea of what is their initial behavior. Then we have our model priors, models and model priors. Then we define the arrays for which model was chosen and the history of the objective function. That's basically it. And then, again, when we run the warm-up phase, we run all three models. When we run the exploration, we pick the model that we expect to give the smallest predictive uncertainty. So this is the typical output of this process. So this is the first step of warm-up. We evaluated all three models. All three models gave us predictions. So obviously the model that has linear and power law segment gives us the value of the linear power law parameter. The model that has two linear segments give us the values for two linear segments and the crossover point. The model that has two power laws gives us the prediction for the two power laws. So at the same time, all the models gives us the updates for the length, scale, and noise. I mean, that's why they're Gaussian process models. So we do it one time, we do it second time, we do it third time, and then we are going from the warm-up to the exploration. And during the exploration, the behavior of the system becomes different. So now we choose just one model. Once we've done this model, we update its parameters and we see what happened. So in this case, you can clearly see that the first model chosen was model number 1. This is incorrect model, so it is the linear and power law. The true model is two power laws. And you can see what the prediction is. So it said that this is our measurement points. This is our reconstruction. This is our uncertainty. This is our acquisition function. And the acquisition function for the first model says that the next measurement should be done here. Excellent. So let's go for the second step. So in this case, it decided that it should choose the model number 3. So model number 3 happens to be the right model. But of course, we don't know that, but see how things are going. So the model number 3 gives us this form of reconstruction. Model number 3 suggests that the next point to do the measurement should be here. This is where it has the maximum uncertainty. But the reward it gives us is also highest for the model number 3. So it thinks it's the best one. Let's go to the next step. So in this case, what happened is that the epsilon greedy algorithm kicked in. So rather than continuing with the model number 3, the algorithm have chosen the model number 2. And since it is the epsilon, I mean, because sometimes we choose the wrong model to make sure that we explore all the variants. So look what happened. So here the acquisition function is going from, say, 0.17 to 0.35. Here, the acquisition function clearly become much larger. So this model does nearly not as good prediction as the previous model. And you can see it here because all the characteristic aspects of the poorly converged Gaussian process are visible. You see that these segments are kind of like sausages, they're almost constant. And the function goes down at the measurements, so the kernel length is pretty small. And you can see it actually here as well. Our k-scale become pretty small in these locations. So nonetheless, it basically told us, you know what, first of all, this model does look very well. And secondly, you should return back to the model number 3 because it gives us the best prediction. Lo and behold, we chose the model number 3. Again, it works much better. The acquisition function has a maximum here, kind of close to the jump. Therefore, we choose the next location for this point. So if you follow this iterate process, so now we determined, again, chosen the model number 3. So the epsilon greedy did not kick in. So the maximum is now here. So it kind of feels like we determined the position of the jump reliably enough. So now the uncertainty is concentrated in these locations. And then if you continue this process, you will see how the algorithm tries to explore this hypothesis. Sometimes it chooses the one that it believes to be the best one. Sometimes it chooses the one randomly. But in the end, you ultimately converge to the right answer. And this is how this process is looking on the exploration of the medium uncertainty versus the exploration step. We started from the wrong model. It actually had a pretty low uncertainty, and that, of course, doesn't tell us much because, again, the uncertainty can be low even if the model is incorrect. Then it explored the right model, and interestingly, uncertainty was growing. It explored alternatives. So this is the part when the model kind of assimilates new data and the predictions are off. And then it starts to actually converge because you actually build the right model that actually fits the experimental data. So then what you can do with that, you can look at the history, so our record, what model worked out more often. So it looks like it was model number 3. And you can compare the fits by all 3 models. So notice that the model number one, which is linear, I mean, so you see how the parameter space was explored, the seed points, the experimental points. So you see that the model number one, it didn't work particularly well, but everything said and done, it gave us some idea about something close to the reality. Model number two, which is too linear, simply fails. So it cannot capture this type of behavior completely. You see the characteristic signatures that things didn't work out particularly well. So model number three, which happens to be the ground truth, worked great, as it can be expected. So this is all I wanted to show today. So as usual, I strongly encourage you to play with the notebooks, because as you can notice with the hypothesis learning, it would be impossible to understand what it does without having a pretty good grasp of the basic principles and the logic of the other notebooks. So let me know if you have any questions, either kind of directly or by chat. And while you are thinking, so in the next lecture, we are going to make another, it's not a detour, it would be a kind of a topic that closely connects both to the way we analyze the data after the experiment and the way we'll run the active experiments using the deep kernel learning. And this topic would be the variational autoencoders. So variational autoencoders, before we go there, so variational autoencoders are absolutely foundational to the machine learning, because they introduce the concept of the intrinsic manifold inside your data. So this is also a fairly difficult to understand concept. So during the next lecture, we are going to explore in detail what are the autoencoders, how they operate, how do we interpret the results of the autoencoder-based experiments on the spectral and on the spectral or imaging or scattering data. So I'll show you example for EELS, for structure, and for the 4D stem. And then, as you can guess, going after that, we will see how the autoencoders can be combined with the active learning to build the deep kernel learning models. And based on my experience, the simple Bayesian optimization is great when you need to do something like tune the microscope or find the optimal setting for the characters or resolution. It is not sufficient for exploration of the image spaces, or analyzing the combi libraries, but deep kernel learning can do that. So speaking about the questions in the chat, so was the selection of the model one deliberate? No, that was just a way we set the random seed. So it's something that you can experiment and see how the algorithm converges. So for the second question about the selecting of the best performing model from the warm-up phase, the answer is that you remember that when I showed the example of the Bayesian optimization, the message was that we can easily get trapped in the wrong minimum, right? So the same danger appears if we have the finite list of models. It's very easy to get trapped in the minimum corresponding to the essentially the wrong model. So that's the reason why we have to balance the exploration and exploitation. The way we use the balance exploration and exploitation in the Gaussian process is by this acquisition function, because ultimately we operate over continuous parameter space. So in the hypothesis learning, our action space is basically the number of hypotheses. So it is a discrete space. Each of the hypotheses comes with its own parameter space, and it can be different. So one model can have 2 parameters, other model can have 10 parameters. One model can be the numerical model, another model can be basically the equation. So unfortunately, the predictive uncertainty is not a good matter. It's not a good measure of whether the model is correct or not. So if the model is absolutely correct, it of course would be 0, but it can be pretty small and the model can be wrong. So we have seen several examples of how it goes on. So the way to make it better is to add the element of the exploration, and the way you explore if you have a discrete list of opportunities is basically by epsilon gradient. If the list of possibilities become very large, then it becomes different. Then there are ways how you essentially use something similar to the policy gradient and the reinforcement learning. But if the list of models is small, as it is the case for the real world examples, in some sense, it doesn't matter where you start. You just need to go through the cycle of the epsilon gradient prediction several times. And then you can be sure, or at least have a high probability that your approach have converged to the right model. So does it make sense? Okay, sounds good. But generally, as I said, the best thing you can do to understand this is basically experiment with these models, because there is a good reason why I give this tutorial from the perspective of the physicist, because unless your background is computer and data science on the fairly advanced level, these concepts, at least to my knowledge, are not a part of the regular physics curriculum. And if your background is data science, then it would be fairly unusual to simultaneously have the background in the microscopy or specifically physics problem. So many of these fields are, as I mentioned in the beginning, are all of the few years old, which of course makes them ultimately useful. Okay, this being the case, let's stop the lecture for today, because, I mean, among other things, now there is the biggest meeting of microscopists in the US, the Microscopy Microanalysis Conference. So I guess for me, it's time to stop talking and start listening. So thank you all for attending, and see you all on Friday. Bye.